Regarding your midterm, you should talk to me afterwards. Okay, last time we talked about linear hashing, so let's go right there. So to remind you what linear hashing does, the difference between linear hashing and extendable hashing is that it does not split or overflow bucket when it becomes overflowed. Rather, it split or overflow bucket in a round-robin fashion. It proceeds in round. In the current round, let's say we're in the level round. Level is a variable, right? This can be 1, 2, 3, 4, so on and so forth. In this round, we have this many green buckets. How many green buckets we're going to have? To the power times level, to the power of level times n. Why? Because the hash function, the hash family we're using is what? Do you remember the hash family we used to construct linear hashing? So that's the hash family we use. Level 0, level 1, level I. Right? So at the level I, how many buckets we have? We have 2 to the power of I times n number of buckets. Now, those are your green buckets. Those are your green buckets. And the red buckets are those ones from the current level that have been split. In other words, in this current level 1, 2, 3, 4, 5, I have seen 5 overflows occurring somewhere in my hash index. That's why I have split 5 green buckets. And those become my red buckets. And each time you split a green bucket, you produce a red bucket, which is the green bucket itself, that becomes red, and a new corresponding blue bucket. What's going on is this guy, the blue one and red ones, they are using now level plus 1 hash function, rather than the current level's hash function. But the green ones are still using the current level's hash function. But the red and blue buckets are using level plus 1's hash function. Okay? So that's the only difference. And when you finally reach here, when you have split all the green buckets, meaning you have, imagine you have red buckets all the way and equal number of blue buckets down below, you reach the end of the current level, you go to the next level, you reset and move the next pointer to the very top. Okay? And you know exactly at this time you have how many buckets. Well, you have this many red buckets by that time, and you have the same number of blue buckets when this pointer reaches here. Why? Because every time you split a green bucket, you produce 1 red and 1 blue, and you have 2 to the power level number times n number of green buckets to begin with. By the end of the day, when you have split all the green buckets, you have equal number of red and blue buckets. If you do a simple calculation, this gives you what? This gives you this many buckets. That's precisely the number of buckets correspond to the hash function from the next level. So it's a really clever construction if you think about it. Okay? That's essentially correspond to so imagine this is here, and by the end of the day I will reach exactly the next level. I will reach right at the next level. Okay, now I'll give you some examples. Let's look at this example. So initially, this is my hash family. This is my hash family. By the way, if you look at this, what's going on here is initially what's the value of n? What's the value of n? For this particular case, what's the value of n? It's 4, right? N equal to 4 in this case. Why? Because you level 1 hash function produce 4 buckets. This will be equal to 1, which means n must equal to 4. Okay? To have 4 buckets. So n equal to 4, and that's why now this gives you what? This one should give you 8 buckets. Level 1 hash function should give you 8 buckets. When you have n equal to 4 and n equal to 8 and 16, essentially what you are doing is similar to the extendable hashing. You are looking at last 2 bits, last 3 bits, last 4 bits. That makes sense as well, because every time when you go from one level to the next level, you multiply the number of buckets by 2. That's essentially same as looking at one more bit in the modular operation. Double the size of the bucket is the same as looking at one more bit of the hash value when you do the modular operation. It's the same thing. Right? Because we're working with binary numbers. When you move out one bit, that's essentially double the size of the output. Okay? Now, so this is my current level. This is the initial state of the index. So I'm at level 0 and I have these values there. By the way, again, these values, they are not the value of your search key, rather they are the hash value of your search keys. To make the illustration easier to understand. So they are, they show the hash value of your search key, not the search key value itself from those data entries. Okay? So those ones from the first bucket will have the last 2 bits equal to 0, 0. Those ones from the second bucket will have last 2 bits equal to 0, 1. From third bucket equal to 1, 0. The fourth bucket equal to 1, 1. That's the initial state of your index. And all of these buckets are in what color? Green color, right? All of these are currently in green color. You have no red or blue buckets. Okay? Now I insert 43. Again, this is the hash value of your search key being inserted. So the hash value of this search key equal to 43, which translates to that binary number on top. Since you are in the current level, meaning that you will check the last 2 bits. So 43 goes where? 43 goes to the last bucket. That's 1, 1. You follow me? And that results in an overflow like this. But in linear hashing, whenever you have an overflow, what do? You split the next bucket. And which is the next bucket? Currently, the first bucket is your next bucket. So you split that. By splitting, the splitting operation actually is the same as extendable hashing. Meaning that you redistribute the entries in the bucket to be split into 2 new buckets by looking at one more bit from their hash values. So instead of looking at 2 bits, now you look at 3 bits for all the entries in the bucket to be split. And you distribute them accordingly. In other words, this is your red bucket, this is your blue bucket. And initially this was a green bucket looking at only the last 2 bits. Now both the red bucket and the blue bucket will be looking at the last 3 bits. Why? Because they are using the next level hash function, which is this hash function now. You follow me? Okay? That's why 32 stay on top. Why? Because the last 3 bits to 32 is 0, 0, 0. And these two, 44 and 36, come here because the last 3 bits of these 2 guys are 1, 0, 0 instead of 0, 0, 0. But they were together in the first bucket at the beginning because the last 2 bits of them are 0, 0, all of them. Question?
Why do we split a different bucket than the one that's overflow?
That's exactly the one. If you think about what extendable hashing is doing, what extendable hashing does is whenever you have an overflow, I will split that bucket, the overflow bucket. That's pretty much the strategy you were proposing. And the problem with that is if you have a really skewed insertions sequence, you end up splitting that bucket all the time. You end up doubling the size of your output all the time. Eventually, this overhead of using a really expensive hash function outweigh the benefit of having no overflow buckets. So the intuition behind linear hashing is, okay, yes, there is overflow in that bucket, but I do not split that right away. I split all buckets in a round-robin fashion. So eventually, I will come to you and split you. And by doing so, avoid the problem of doubling the size of the output whenever there's an overflow bucket. Here, you increase the size of output by only one bucket instead of by 2 times, as what happened in external hashing. Okay, let's continue the example. Let's imagine after this operation, I did some furthermore insertion and some furthermore overflows. My pointer reached here, which means you have exactly 2 more overflows somewhere. That results in splitting this, and come down here. Okay, and we reach a state like this. Is that okay? Now I'm gonna insert 50. So this is an interesting case, right? This is an interesting case. When you insert 50, which bucket should 50 go into? Should 50 go into this bucket or the corresponding bucket for this bucket? This and this, they were produced by the same green bucket to begin with. This is your red, this is your blue. Okay? You follow me? Meaning that if you look at the last 2 bits of these guys, they will be 1, 0. However, because of the split operation, these 2 buckets now look at the last 3 bits. So whatever is staying here will be 0, 1, 0. Whatever comes here will be 1, 1, 0. In other words, when you try to insert 50, what happens is you look at the last 2 bits first, because you are still in the current level, which is level 0. You look at the last 2 bits. Last 2 bits tell you it's 1, 0, so it should go here. Once you realize that, you know it's one of the red buckets. As soon as you realize that, you switch to the next level hash function to find out where this guy really belongs to. So first, let me repeat this, right? First, you use the current level hash function to figure out whether it belongs to a red bucket or green bucket. If it belongs to a green bucket, you keep on using the current level hash function to find out which bucket it belongs to. However, if you realize this guy actually goes to a red bucket, that's the moment you will switch to using the next level hash function to figure out whether it goes to a red or blue bucket. So in this particular case, 50 is one of the red buckets. So you should use the next level hash function to figure out whether it's here or here. And in this case, it's 0, 1, 0, so it stays here, which means you will have an overflow right here. And once you have overflow, what do? You split the next bucket, which is this bucket. Which means you will create a blue bucket here. And looking at redistribute these entries by 0, 1, 1 and 1, 1, 1 instead of just 1, 1. So you will end up like this. So these guys will be redistributed. Some will stay here because the last 3 bits is 0, 1, 1. Some will come here because the last 3 bits are 1, 1, 1. By this time, you have split all your green buckets. And it's guaranteed by the proof over there, you have double the size for the number of buckets. You have double the number of buckets you have. And you enter the next round. You move the next back to the top. You officially enter the next level. You officially enter the next level. So linear hashing has been extensively used beyond database system, right? In fact, When I was a student, I was interviewed by Google for internship. The first question they asked me is how to design a hash function. Then they went on asking linear hash. That's pretty much this stuff. Okay? Linear hashing. So it's an extremely useful technique in practice to deal with a skewness in your workload when you try to build a hash indexing structure. A lot of you know Redis, right? Redis is a key value store. It's essentially a min-memory hash table, right? For any min-memory hash table and things like that, if you try to maintain balance under dynamic insertion deletion, you will resort to something like this: linear hashing or extendable hashing. Okay. That's it. I think that's it. Okay. The point to notice is the last insertion produced an overflow and I split that, but I still have an overflow that I didn't handle, right? I didn't handle in the current round, but that's okay. Question asked earlier, in my response to the question asked earlier, the point of linear hashing is eventually your turn will come. Your turn will come. So, in other words, if you think about this from an intuitive manner, extendable hashing is really a greedy algorithm. Greedy algorithm means that whenever you see a profit, you go for it. So whenever there's overflow, I address that. I split the overflow bucket. But a greedy algorithm can often lead you to a really dramatic situation where if you're really trying to be too greedy, right, that's essentially the way to look at extendable hashing. Linear hashing, on the other hand, is a little bit more conservative. It's a little bit more conservative. It's like, okay, I don't counter-strike right away. I wait a little bit, and eventually I will handle that case as well.
So, are there any times where we might choose extendable hashing over linear hashing?
Well, that's a good question. So, I think typically people go with linear hashing because, yeah.
But you also said they use this technique.
Because in practice, what people realize is extendable hashing works okay in most cases, but if you run into a really bad case, things can go really out of control. And linear hashing, on the other hand, because you are playing conservative, a conservative strategy, in most cases you are okay. In some cases, you are not as good as extendable hashing because you may have overflow buckets. But if you look at all possible cases you're going to handle on the average sense, linear hashing is better. You have a question? Yeah.
So just theoretically, so as an adversary, we can still like
of course.
Sequence.
Of course.
That.
Of course. You can always design an adversary that beats this as well. That beats this as well. What happened is, what's the worst case? The worst case is I always insert into the bucket the right, depending on how you count after and before, right? Right after the bucket to be split, and I always insert to over there, so you have a really long overflow chain in that bucket. And even though, yes, you say you're going to come back to that, but you are really splitting a lot of unnecessary buckets, and this one overflow chain, even though you come to split it, producing two new buckets is not good enough to handle the overflow chain. Right?
And a lot of empties.
Yeah, a lot of empty, yes. So the way to address those problems is to use something called hybrid hashing. We will talk about that later on. Okay. Remember this keyword, hybrid hashing. The search algorithm, I don't think there are examples, but I want to skip this. Because the search algorithm, essentially, let me just quickly highlight the search algorithm. The search algorithm, basically, you always use the current level hash function first, and then find out whether you are in a you are in a red bucket or in a green bucket. If you are in a red, then you are done. You just try to find the value there. If you end up in a red bucket, you switch to the next level hash function to find out whether you're really in the red bucket or a blue bucket. That's it. But you may wonder, how do I know I'm in a red or green bucket? Well, you look at the bucket you are being hashed to, compare that bucket against the next pointer you have maintained. If you come after the next pointer, that means you are in a red bucket. If you come ahead of the next pointer, you are in a green bucket. Do you follow me? Okay, let me give you an example. Search 44 and 9. 44, so if I use, so this is the easy case, right? Because I haven't split anything, so everything is green bucket. There are not even a single red bucket. So I just use the current level hash function, which is looking at last 2 bits. I go to the first bucket and down. If it's like this, okay? If I search 44, what happens? If I search 44 now, I know I use the current level hash function first, which is looking at last 2 bits, and end up in the first bucket, which is the red bucket. I know I should use, at this time, I should use the next level hash function to locate 44, which is looking at last 3 bits, which become, you look at 0, 0, and 0, 3 zeros. And that tells you 44 is actually in the blue bucket instead of the red bucket. How do you figure out it's a red or blue bucket, red or green bucket? Once you are in the first bucket, you check against the position of the next one. Well, I'm like after you, so I must be a red bucket. So at this point, I should use next level hash function to locate this guy. That's all. I think the only thing we didn't discuss is the deletion procedure, which is exactly the reverse of the insertion. Okay, it's exactly the reverse of the insertion. I leave that for you to ponder a little bit, to think about how the deletion is supposed to work. Okay, and if needed, I will give you some small discussion at the beginning of the next lecture. Okay, but essentially, it's exactly the opposite of the insertion procedure. Now let's move on to the next lecture. That's essentially, the next lecture will be you product 4. The next lecture is about accidental sorting. So sorting is the foundation of computer science, right? Pretty much. I think for a lot of you, including myself, the first problem I encountered that's really a computer science problem rather than just a typical programming assignment is sorting. Because intuitively, most people, when you give them a sorting problem, the first time they were introduced to this problem and they know little about computer science, the most natural and intuitive solution is bubble sort. You take the first one, compare against all the remaining one, you swap, and so on and so forth. And the complexity of that is what? Is n plus n minus 1 plus n minus 2 plus 1. Why? Because the first one you spend n times, you check, right? You read itself and compare against n minus 1 other items, so it's n. The second one, you don't have to compare against the first one because you know by the time you move on to the second position, the first one is already the smallest after the swap operation. If any, you may not need to do a swap because if the first one indeed is smallest, but you do have to check against all the other items to confirm that. So you come to the second one, you don't have to compare against the first one, you only need to compare the remaining ones. That'll give you the n minus 1. Okay, that'll give you this. And this is this German guy named Gauss. He solved this problem when he was like 5 years old, right? It's like, I think I always mention this story. So he was in a kindergarten and the teacher got really bored. And the teacher is tired of, after long, they're tired of playing with kids. And she basically said, okay, I'll give you this problem. Go solve this problem. 5-year-old, right? And she used 100, right? So what's the... Okay. She figured out this problem. And she expects the kids to spend at least 20-30 minutes to solve it, right? Because 5 years old, what can you do? 1 + 2 = 3, 3 + 3 = 6. This will take a while, right, for them to do, right? But unfortunately, to her surprise, Gauss was in her class. And he solved the problem in like 2 minutes. And the teacher was like really surprised. And the way he solved it is, right, you see, this pair gives you 1 having 1. And you have about 50 such pairs, a multiplication you're done. I mean, to his credit, right, to be able to do multiplication at that age is still a challenge, right? But still, you know, once you figure out this is easy, right? So same thing here. If you just pair this up, and you can kind of solve this problem. So roughly is, so in big O notation, that's essentially this. You have roughly n minus 1 half this many pairs of n. That's essentially the answer. Okay. So roughly, to be precise, it's half of n squared. Oops. So it's half, but in big O this is n squared. Okay, that's power source. So most often, the first time you were introduced to the sorting problem, that's the code I wrote. These are days. When the first time I was asked to write a program to sort a sequence of number, I used bubble sort, and I wrote that program in Pascal. That was a really popular language back then. And it's a small sequence of numbers, so performance-wise, I didn't notice anything wrong. It's like a few hundred numbers. It's like really fast, right? But if you try to run that over not even a million, right? If you try to run that over 100,000 numbers or 10,000 numbers, n squared becomes really big. It will take forever to sort them, right? So people invent many different sorting algorithms to do this. One of the most famous one is what? Is quicksort. Quicksort, the idea is very simple, right? You choose a pivot, a random number from your sequence, and then you scan through your sequence. The ones smaller than this number you have chosen, which is your pivot, goes to the left. The one bigger goes to the right. Now you know these numbers are bigger, less than this. These numbers are smaller, are larger than this. Then you recurse. You do a recursion. You call the same procedure on the left sequence and right sequence. On expectation, if you're really lucky, you always choose the median. Always choose the median, the number that's in the middle from the sorted sequence. If you always choose the median as your pivot, each time your sequence is reduced by half. The size of your sequence is reduced by half. Right? So initially you have n of that, and this is your pivot, and this become half of n, this become half of n, then you recurse. And if you're really lucky, when you recurse, you choose the median again, and this becomes n over 4. And so on and so forth. And you terminate when you only have one number left. How many iterations you have to do in order to reach that state? Well, if you're really lucky, each time you reduce the size by half, it only takes you log n levels, log 2n levels to reach that state. And at each level, no matter how many, you can run this in parallel. Let's forget about parallelization. Look at the total number of operations you have to do across all these sub-sequences. In this level, you only have one sequence. What's the cost in this level? Well, let's assume choosing the pivot is just randomly pick one number. Okay? But once you have the pivot, you have to scan the sequence and compare against this one. The cost is median, n, right? Scan and compare, n. In the next level, yes, you have two pivots. You have to scan two subsequences, but the cost of each of them is half n. So the total is still n. So in each level, the total number of comparison from all subsequences is still n. and you have log n levels, so the total cost is what? It's n log 2n. Of course, in my analysis, I assume kind of like a best case, you always choose the median. If you're not lucky, you don't choose a median in some levels, then you may need more than log 2n levels to reach the termination state. But nevertheless, each level, the total comparison operation, total number comparison still is n, right? Still is n. It's just that you may need more levels. But using a randomized argument, you can show that this on expectation, this is roughly n log n. That's merge sort. What we are going to talk about here, though, if you think about this algorithm, what's the problem of this problem? What's the problem of this algorithm? Well, if this number fit in your memory, that's okay. But if they don't fit in memory, suppose my memory can only hold this many numbers, all the things after, let's say I can hold about this many in memory, and n over 3 of them is on disk. What is the problem of this approach? While you're paying many IOs to scan through these numbers. Do you follow me? And in this level, in the first level, it's not too bad because I can read in this page by page. But as soon as you're here, when you have many subsequences, you're paying random IOs among these random subsequences. So your IO cost will be a dominant cost. It will be more than n log n. So that's the problem. So we want to find an IO efficient algorithm to solve this problem. That's essentially the merge sort. We run out of time, so we'll continue next time. So one quick note, on Thursday lecture, we have an invited speaker, a professor from University of Washington, and she will talk about her project on big data management. I will make an announcement, and all of you should come. It's a regular lecture, but it's an invited guest to talk. Okay? I will send you the details. All right, thank you.